Okay, IBAISL2. Today we are starting chapter 8, which is another statistics chapter, and we're going to talk about Spearman's correlation coefficient. So you're going to see that word correlation. It's very similar to the correlation we've been using, which is the Pearson's correlation coefficient. Spearman's correlation coefficient, first of all, is R sub S. Pearson's is just lowercase r, but Spearman's is now R sub S. The main difference is that Spearman's is very appropriate when your data is non-linear, when it looks like there's some sort of strong correlation that's not a straight line. So it still works the same way that it can be all the way to +1 and all the way to -1 and anywhere in between. If you had a perfect Spearman's of +1, that would mean that the data is strictly increasing. So it always moves up as you move to the right. A -1 value would mean that it is strictly decreasing, and it always moves left, or it always decreases as you move to the right. Those situations are called monotonic data, when it's constantly increasing or constantly decreasing. So just a visual to help you guys with the difference between Spearman's and Pearson's. This first graph here, how you see there's like a very strong linear positive correlation. This would have a strong Pearson's, but also a strong Spearman's. So Spearman's works for linear data. I think just if it tends to look linear, you should use Pearson's because that's the standard for linear data. Now this second graph over here, this one, it is not linear. It doesn't make a nice straight line, but it does have a nice correlation to it. It just is like a curved correlation is all I'm going to say. It's like, an exponential or something like that. So if you tried to fit a line of best fit to this, you could do it. Please make a line. And it would be something like this for the data, but it's not very good. So because this is non-linear, this would have a weak Pearson's, but a strong Spearman's. So because it's non-linear, like you would want to use Spearman's and not Pearson's. So I'm going to show you guys how to find Spearman's rank correlation coefficient. There's a lot of commonalities about how you find it. We're still going to use a TI-84 graphing calculator, but you don't exactly put this actual data into the calculator. What you have to do is rank the data. So here's how you make rank data. So we're going to rank the x's and then rank with the y's. So to rank the x's, you look at the x's in the top row and you decide what is the largest x. So when you look at all of these values here, you go, okay, what's the biggest number? Okay, 45 is the biggest number. So down here, when I set up here, I'll put some lines so this is correlated. Correlated, get it? 45 is the number one top value. So right in this spot right here, you're going to put the number 1 because it's like the first rank. Then the next biggest value is the 34. So in this spot, we're going to put the number 2 because this is the number 2 highest value. Then I think 29 is number 3. And then it gets a little bit interesting because if you look like what's lower than 29, you see that 23 and 23 are the next one. So anytime that you have to split, if there's double values for the split, what you do is say that, we already got first, second, third. So this would be the 4th and the 5th, and then you divide it by 2. So each of these would be the 4.5th. So what you do is put a 4.5 in both of those spots. 4.5, 4.5. So we're up to, here, let me erase this so I'll highlight. 1, 2, 3, 4, and 5. So the last one is going to be 6. So the 17 here is going to be the 6th rank. So it's like you have 1st, 2nd, 3rd, 4th, 5th, 6th, but because the 4th and 5th were the same number, you average them to get, they're both the 4.5th. Do the same thing with the Y's. If you look at it, I think that 14 is the biggest one. So you put a 1 right here. Then 12 is the next biggest, so a 2 goes here. Then, so for these two 11s, those would be the 3rd and 4th. So if you average 3 and 4, you get 3.5. So both of these are 3.5. Not 35. My jolly. So that was 3rd and 4th, and then 5th is 10, and then 8 is the smallest one, so this gets the 6th rank. Now, what you do is you put this entire top line, so all of this is going to go into your L1 in your calculator, and then all of this is going to go in your L2. Then you'll see in the other video I posted for you guys, you're going to go to stat, and then arrow over to tests. And then you got to scroll down for a little while. It's past the numbers. It's the alpha F linreg t-test. So when you run that linreg t-test, you'll see a bunch of numbers. Here, let me run it. So once again, reference my video about the settings for the linreg t-test. But once you have it set properly, you don't have to change it. This is a negative. So once you run the linreg t-test, scroll down to the bottom. There's more information past just the initial screen. And you'll see like an S, a B, an R squared, and a very bottom one is the R. So that R that you see is negative 0.956. So we'll say RS is negative 0.956. The calculator doesn't say that it's R sub S, it just says R. But remember that when you run a linreg t-test, you're finding Spearman's R, not Pearson's R. What this means is that there is a strong negative correlation between the two things. So that means that the more time you spend training, the less time you're going to run the race in. Like the time to run the race will decrease as you spend more time training, which makes sense. So more training, equals less race time. I'm going to do one more example of Spearman's rank correlation for you guys. This one says that Lindsay went out to try a bunch of burgers in Portland. So she hit up all the best burger spots, and she ate 9 burgers. So she just called the burgers A, B, C, D, E, F, G, H, I. But then she ranked them. She said, like, okay, burger E was number 1, and then the second best one was G, and then the third best was B. So they're already ranked. This is your main clue that you should be using a Spearman's rank correlation coefficient. And she also put the cost of how much the burgers are. So how much she liked them, ranked in order, and how much each of them cost. So the question sort of becomes, is there a correlation between how tasty they are and what they cost? Like, does a tastier burger cost more? Are they correlated? We can't use Pearson's in this case. So because she already ranked the burgers, like it's not quantifiable data, it's just ranked data. So we can't use Pearson's. It doesn't make sense. We can use Spearman's correlation coefficient. So once again, you're going to want to rank both sets of data. So the top one, the X, was the rank, and then the bottom one was the cost, and this will be Y. The X's are already ranked, so that's going to be the same order. It's just going to be 7, 3, 4, 6, 1, 9, 2, 5, 8. Yeah, she already ranked them for us. So all we have to do is rank the costs. So you look for the highest costs. That was the 850. So this is a 1. Then the next highest was the 745. That was 2. And then the next highest was the 650, and so on. This one was the 4th. This one was the 5th, 6th, 7th, 8th, 9th. So the rank and the cost are both ranked. There was no doubles in the cost, so I didn't have to split any ranks. They all just were what they were. So then you're going to punch this all in to L1 and L2 and run your lin-reg t-test. And when you do that, scroll down to find your R value is 0.8. I believe this follows the same, like there's all these words that describe the strength of the correlation. They call 0.8 moderately strong. I think this follows our table that we had before. Don't quote me on that, but yeah, I think moderate, or was strong anything above 0.75? At any rate, this is a moderate positive correlation. Now, what does this mean in terms of the burgers? So there's a moderate positive correlation between tastiness and price.